A star's life cycle is much like that of our own. It is born, ages, evolves, and eventually dies just as we do. A star may live for billions of years, and unlike humans, a star's life cycle has nothing to do with its lifestyle or heredity. It's all about size. All stars evolve the same way up to the red giant phase. The amount of mass a star has determines which of the three life cycle paths it will take after the red giant phase. In this video, we will explain the different life cycles of low, intermediate, and high mass stars. All stars begin as a nebula, a cloud of dust and gas, composed primarily of 97% hydrogen and 3% helium. Within a nebula, there are varying regions when gravity causes this dust and gas to clump together, causing the cloud to become more dense and also creating a greater gravitational attraction of other atoms. Because there are so many reactions occurring within the star-forming region, a protostar, which is the earliest stage of a star's life, before fusion commences and when gas is rapidly falling onto it, is not considered to be very stable. In fact, a protostar is not a star at all, and in order for it to achieve life as a star, the protostar will need to achieve and maintain equilibrium. In this case, equilibrium is a balance between gravity pulling atoms towards the core, referred to as accretion, and gas pressure pushing heat and light energy away from the core. In other words, equilibrium will be reached when gas pressure pushing outward is equal to gravity pulling inward. If gas pressure remains less than gravity, the critical temperature of 10 million Kelvin is not reached in the core of the protostar. It ends up being a brown dwarf. This mass will never be referred to as a star. Rather, it is a planet-like orb of helium and hydrogen with a mass less than 0.08. Critical temperature of 10 million Kelvin in its core is reached. It will start fusing hydrogen into helium. This is what astronomers identify as the official birth of a star, and it's also referred to as the pre-main sequence phase. Once equilibrium and nuclear fission is achieved and the protostar is no longer accumulating mass, each layer, the pre-main sequence star, can finally support itself. It will cease to collapse further and is said to be in hydrostatic equilibrium. When this stage is reached, a main sequence star is born. A main sequence star is a star in which nuclear reactions fuse hydrogen into helium in the core at nearly a constant rate. Our Sun is said to be in hydrostatic equilibrium and is expected to spend 10 billion years in this phase of its life. It is in this stage the star will live out the majority of its life. This is also where its mass comes into play in determining its life cycle. If the mass of the young main sequence star is between 0.08 and 0.4, it is considered to be a low-mass star, called a red dwarf. Low-mass stars burn cool and dim, consuming their hydrogen fuel very slowly. Eventually, when their fuel burns out, in approximately 15 billion years or more, they change into hot but small white dwarfs. A white dwarf is the remnant of a low-mass star that has consumed all its thermonuclear fuel and contracted to roughly the size of Earth. In this stage, they will quietly just fade away and burn out. A white dwarf is a dying star. Now let's suppose the main sequence star has a mass of 0.4 to 8.0. It will be considered an intermediate mass star. Here's where it gets different. These stars burn their hydrogen fuel a lot faster than a low-mass star, but tend to have a longer period of stability. Our Sun is an intermediate mass star and, as said before, will burn steadily for some 10 billion years. But when it finally runs out of hydrogen fuel and gravity grips the core, the star will grow hotter, causing instability. Its layers will no longer support themselves, and they will expand and consume anything nearby in its fiery demise. This is when the star becomes a red giant, a large cool star with high luminosity. Gradually, it sheds its material into space and collapses in on itself, slowly shrinking into a very dim white dwarf. And as it cools even more, it turns into a black dwarf, a non-radiating ball of gas. However, if the intermediate star has a mass of 8 to 25, it will shrink to a neutron star. A supernova happens when a neutron star is created. Neutron stars are very compact, dense remnants of a star, composed entirely of neutrons which prevent further collapse. The size of a neutron star is about half that of a large city. These stars utilize carbon burning, which occurs when the helium in the core is gone. By now we know the core needs to maintain its critical temperature to keep the gas pressure up, otherwise the star cannot resist gravity. When carbon burning does occur, iron is formed. Iron is the most stable of all nuclei and ends the nuclear fusion process within a star. With the decrease in fuel or fusion, the temperature decreases and the rate of collapse increases. Just before the star totally collapses, there is a sudden increase in temperature, density, and pressure. The pressure and energy compact the core further. The compacted core becomes a rapidly whirling ball of neutrons, and that's why this star is now termed a neutron star. High-mass stars, on the other hand, like red and blue supergiants, which are, say, twice the size of our Sun, are those main sequence stars with a mass of more than 25. These stars tend to burn out quickly, sometimes in just a few million years, and they don't die quietly. In fact, it goes out with a big bang called a supernova. After gravity has compacted a white dwarf into a neutron star, and depending on how massive the star, some have become so dense they turn into a black hole. An object whose gravitational pull is so great, matter is literally squeezed into something unseeable, which stretches for miles and weighs an incomprehensible amount. A black hole is invisible but deadly, as it pulls in matter all around it. Even light can't escape. We hope you've enjoyed our video. Thank you for watching.